me to tell all those things first, considering the people who are new to the field of solar physics. Now, the plan of presentation it is divided like this. First is introduction. The introduction it covers solar interior. Sun as introduction, which is covering the sun. And sun, we are dividing into solar interior and then solar atmosphere, and then followed by what is space weather, and finally we have the conclusion. The sun, all of you know, it's an object of great beauty. Sun basically is a star. Most of us we think that, especially in India, even a common man, they think that sun is a planet. It's not a planet. It's a self-luminous, and so it's able to generate its own energy. And so the energy of the sun will come for another, say, around 5 billion years. And so it's a star by itself. The sun looks to be a superstar. As soon as the sun comes, the entire sky is washed away by the sunlight. So from horizon to horizon, you are completely filled with the sunlight because of the scattering of light through our atmosphere. And eventually what happens actually is the stars that are still there, they are blanked out. Stars are still there. If you go above the atmosphere, if you go to space, then even during the morning time, it will be possible for you to see the stars. Now, sun is one of the stars, one of the billions of stars, 100 billion stars in the Milky Way galaxy. And it's an average star. It's not neither a big star nor a small star. And most of the constituents of the sun, it is of hydrogen, and then helium, and only 1% it is consisting of rest of the things. In astrophysics, except beyond the atomic number 2, hydrogen and helium, rest of the elements are called as metals. We don't call them as gases or something like that. So only the atomic number 1 and 2 they are called as gas, hydrogen and helium. Anything which has more than atomic number 3, 4, 5, 6 and so on and so forth, they are all beryllium, lithium, boron, carbon, nitrogen and so on and so forth, oxygen. They are all called as metals, though they are in the conditions of ionized conditions and as well as the gaseous state. Yet in astrophysics, when we refer these elements, anything which is going beyond number 3, atomic number 3, they are classified as metals. And only 1% it is consisting of the rest of the elements like carbon, nitrogen, oxygen and so on and so forth. And these elements, higher elements, they are present almost in the upper atmosphere of the sun. Now, as you know, as we are all aware, if sun is not there, life cannot persist here in the planet Earth. And it's a process, photosynthesis process, okay? So photosynthesis process through which because of the sunlight, what happens is the ingredients to the plants, they are carbon dioxide and as well as water. Plant gets carbon dioxide plus water in the earth, and then it generates glucose in the form of leaves, and as well as it emits oxygen. So this reaction can go only if sunlight is there. If sunlight is not there, as you know that 65 million years back, because of the fall of the asteroid, the complete atmosphere, it was faded out, and because there was no sunlight, and animals like dinosaurs, they extincted. And there were no plants at all, because without the sun, the planets, they cannot do, the plants, they cannot do this process of photosynthesis. And because of that, the leaves come. And we eat the leaves, animals, they eat the leaves, and so the survival of every living being here in the planet Earth is possible mainly because of sunlight. The next one is the physical properties of the sun. Sun is an average star, as I was telling you. It's not a very big star. And you can see the mass is enormous. And radius is approximately 7 lakhs kilometers. 7 lakhs into 700,000 kilometers. And the density, tremendous density. and means distance from the sun, from the earth, it's called as 1 astronomical unit. All of you may be aware of that. 1 astronomical unit, that is 150 million kilometers approximately. And surface gravity, tremendous surface gravity, and temperature is 6,000 degrees approximately in the surface. And now sun, it emits radiations of all kinds, whatever we can think of. Radiation ranging from high energy gamma rays. Unfortunately, this pointer is not working. I see.
Okay.
So high energy gamma rays to low energy radio waves. Okay. So sun is a black body. All of you may be aware. It's a black body, an object which can emit radiations of all kinds. It's an object of great beauty, as I was telling you. It's able to emit radiations ranging from high energy gamma rays to low energy radio waves. And now you can see here, we are sitting on the earth, comfortably we are sitting on the earth, and our earth, it acts like our atmosphere. It is filtering most of the dangerous radiations, allows only the radiations that are suitable for the life here in the planet Earth. Otherwise, our atmosphere acts like two windows. One window allows the radiation in the visible part of the spectrum, and another one allows the radiation in the radio part of the spectrum. So by standing on the surface of the earth, we can observe the radiations from the sun either in the visible light or in the radio light. To study the sun in the visible light, you need to have optical telescopes. In Kodaikanal, we have optical telescope. In Lankavi, we have optical telescopes. And to study the radiation in radio, we need to have dish antennas or arrays of antennas that are situated in the Ministry of Science and Technology in India. It is in a place called Gauri, where you have for 3 kilometers distance and then 2 kilometers T-type array, a huge one, and that has been operated by 4 different institutes, not only Indian Institute of Astrophysics, but Bhabha Research Atomic Center, and then Tata Institute of Fundamental Research, and Raman Research Institute. So all the 4 institutes, they collaborate with having an instrument there. And of course, Tata Institute of Fundamental Research, they have their own radio telescope arrangements in Ooty. Perhaps you may be aware of Ooty radio telescope. And there they have telescope radio arrays to study the sun, radio radiation emitted by the sun. Of course, all of us, we know that you see the energy of gamma ray, it is tremendous. It is more than 100 kilo electron volts. But whereas radio waves, 10 years to 1. You see, the radio waves of the order of around electron volts only, not to the level of kilo electron volts. That means what? See, a single gamma ray photon, it is 100,000 times more energetic than a single visible ray photon. So if gamma ray or X-ray or ultraviolet and then or infrared and all these radiations, dangerous radiations, if they are able to penetrate through our atmosphere, which extends up to a distance of around 600 to 1,000 kilometers from the surface of the earth, then life cannot persist here in the planet Earth. Because that's why we generally used to say we have a beautiful atmosphere. Beautiful, we call it as a beautiful atmosphere. But for the atmosphere, life cannot be possible here in the planet Earth. Of course, we are, as a humanity, we are supposed to preserve the atmosphere. We are not supposed to spoil the atmosphere. Of course, there are those things, the global warming and all. Seriously, they have been taken up in the recent past, and hopefully that we will be able to have a green revolution. The next one, this is a solar structure. Now we are going to see the solar interior. Solar interior is here, is divided into 3 zones. First is core, and then the next is radiative zone, and then the third is convective zone. You can see the convective zone, and then solar atmosphere. Again, the solar atmosphere also, as you go away from the sun The solar atmosphere is divided into three zones. First is photosphere, and then chromosphere. This is photosphere, where you can see the presence of sunspot. This is the surface of the sun, that we will talk about, all the details. And then corona is the outermost atmosphere of the sun. So, essentially, the sun is the core. Inside the sun, it is divided into three zones: core, radiative zone, and then convective zone. The outer atmosphere, it is again divided into three zones. Photosphere is the surface, and then chromosphere above, and then beyond chromosphere, corona. Earth is immersed in the corona. Okay. Now you can see. Now we will see the interior. How the interior looks like. See, the interior. First is the core. You can see the core. The temperature is 50 million degree. Okay. And at 15 million degree, because what happens actually is, you see that core temperature is very high, 15 million degree, density is very high, and then pressure is very high. You know the ideal gas equation, P is equal to NKT. And because of that, what happens actually is, nuclear forces dominate such a volume of density. See, for example, in the same room, if the room is filled with hundreds of thousands of people, then what will happen? We cannot feel the AC. The temperature shoots up. Agree? The temperature shoots up. And exactly like that, when the density goes extremely large there in the core, then what happens is, the pressure, inside pressure, that becomes extraordinarily high. As you put more and more people here, the pressure, inside pressure will develop, and it will not allow further people to come in. Okay? So the pressure shoots up like anything, and because of that, the temperature also goes up like anything. Only at such a high temperature, 15 million degree, then what happens actually is, nuclear forces dominate. All of you know, proton cannot join with photon at ordinary circumstances. Otherwise, you can make proton to fuse with proton here, or you can make hydrogen to join with hydrogen here. It's not possible here. Where the density, such conditions, all those three conditions, the core should be satisfied. So that once the temperature goes to 15 million degree, and at that time, nuclear forces dominate the electrical repulsion, Columbian repulsion between the protons, and then what happens actually is, the nuclear fusion reaction takes place, and the continuous flow of energy. The energy is generated, and that energy keeps coming for billions and billions of years. And the sun is, we are so safe, sun is going to exist for another 5.6 billion years. Okay. And now core is, because the core is, how powerful it is. See, the temperature is extraordinarily high. When the temperature is extraordinarily high, then what kind of radiation that we can expect? Previously I have shown the kind of radiations, gamma ray to radio waves. At such a high temperature, high energy radiations, they will be generated. So gamma rays are the first kind of radiations that are generated at the core, from the sun, generated from the sun. Okay. Now let us go to the next layer. The next layer is this one, for radiative zone. The radiative zone, you see, it functions like an insulating layer. Sun is generating energy. For example, you keep some, if you come to Kodaikanal, it's the temperature is very, very low. Okay, the temperature is very low. It's a hill station. The temperature is of the order of around in the night 8 degrees. And when you like to sit out and then take dinner, okay, and bonfire dinner, then you put a fire. Then what actually, if the fire, the next day if you come and see the fire would have extinguished. Agreed? The fire would have lost its energy to the surroundings. Like that, the energy that has been generated there in the core, suddenly it should not escape out. If it escapes out suddenly, instantaneously, then what will happen? After a few hours, we will not have sun. Sun will be switched off. Agree? So, sun will be switched off. Because whatever energy that has been generated, if it is thrown out instantaneously, then sun cannot last for billions of years. Okay? Billions of years. In Indian numerology, we call it as crores of years. Crores of years. Agree? Crores, or billions, billions of years. So instantaneously it will be escaping out of the sun, and then sun will die. All the fuel will be exhausted. So this radiative zone, it acts like a insulating layer. So the energy that is generated slowly diffuses through the radiative zone, and here the temperature goes down. Okay, and then what happens actually is slowly it goes down when because of it hits with the material here in the radiative zone, and then it loses its energy, and then again it sneaks through the radiative zone, and then by the time it reaches the surface, it takes approximately 15 million years. 15 million years. What do you mean by that? If you assume the sun is switched off now, then the energy generated right now at a particular second, that will exist for 15 million years. It's an amazing thing. So that radiative zone, it does such an enigmatic process, and because of that, what actually happens is the energy generated in the sun does not escape just like that, and it is going to come for such a long time. And here, as the temperature goes down, then what happens is you get X-rays, because as the energy goes down, as the material, as the electromagnetic radiation passes through this radiative zone, it hits up with the material. In the process, it loses energy. So because it's losing energy, then what happens is X-rays and soft X-rays, hard X-rays, soft X-rays, and they're all produced here in this region. The temperature goes down to the level of million degree. Okay? So this is radiative zone. The next one is convective zone. And of course, the radiative zone, again I would like to tell you that it is more than 1/3 of the sun's interior, whereas the core is 1/3 of the interior. Slightly more than 1/3 of the interior is, you can see the cross section. Okay, it is slightly more than the core size. Okay, and then the third one is convective zone. You see here, you can see the temperature drops down. At the base of the convective zone, the temperature is 1 million degree. All of us, we know at the surface the temperature is 6,000 degree. And the distance is, the convective zone, it has a thickness of 20,000 kilometers. And within this 20,000 kilometers, a gradual reduction of the temperature takes place. The temperature reduces from 1 million to 6,000 degree. And because of the temperature gradient, convection sets in. Because of the convection, generally what happens actually is, and the material here, it will be in the form of plasma. It will be in the form of ion. So once the ions are electrical ions, once these electrical ions are convected, then what actually happens is magnetic field is generated. So this is the place where the magnetic field generation is taking place. And if sun is not able to generate magnetic field, physicists will not show any interest to study the sun. And because of the magnetic field of the sun, all of us are interested to study the sun. Otherwise, it will be a blank object. We will not be studying the sun at all. And this magnetic field, it is that's what is going to do the space weather and other things and all we are going to see now. And then the next one is, this is the photosphere, this is the surface, and next is the chromosphere, and then this is the corona. In the photosphere, visible radiation. In the convective zone, it is extreme ultraviolet, ultraviolet, and so on and so forth. And then in the chromosphere, visible ultraviolet, and then infrared. Again, you see the corona, as you go, the coronal temperature will be very high. Again, X-ray, radio, gamma rays, all those things will be produced. Likewise, whatever radiation that has been produced here, and they all come out like that, and so sun behaves like a black body emitting radiations of all kinds you can think of, ranging from high energy gamma rays to low energy radio waves. This is the sun's interior. Next we will go to sun's atmosphere. The sun's atmosphere, as we told earlier, it is again divided into three zones. First is photosphere, next is chromosphere, and beyond chromosphere you have corona. So now, this is the surface of the sun, which Zahira was pointing out that they have been studying sunspots, and they have been plotting the sunspots. And so in Kodaikanal, we have been doing it ever since 1891, one of the oldest observatories in Asia. Because Britishers, when they were ruling here, next to the Greenwich Observatory that was started in the year 1851, they wanted to establish another observatory. And so they thought that Kodaikanal is an ideal location because of the weather conditions. The hilltop, the sky transparency is beautiful, and because of that, the seeing condition will be very good. And so they selected Kodaikanal as another site for solar studies. Ever since then, the solar studies are carried out at Kodaikanal Observatory. It's one of the oldest observatories of its kind. And now, the surface of the sun, you are able to see the sunspots, and photosphere is the disk, whatever we see. Now, whatever we see the sun through the naked eye, we are able to see the photosphere. And we know the sun is a gaseous object, it's not a solid object like the earth. And because of that, sun's surface, this is the earth's surface, it's a solid rigid surface. Okay, we are standing on the surface of the earth. But whereas sun's surface, for sun's photosphere, it extends up to a distance of 500 kilometers. You can see. The temperature is around 6,000 degree Kelvin, 5,780 degree Kelvin, 6,000 degree Kelvin. It looks as if, that if you watch closely, if you observe closely the sun, it looks as if the entire sun is wound up with magnetic lines of force. As I told, the convection zone, it generates magnetic field, and that magnetic field lines, they coil around the entire sun. In some of the regions, what happens is, there's a magnetic buoyancy, the magnetic bundles, they breaks out, and then sunspots are formed. Sunspots are formed. Okay? So, this is the magnetic activity of the sunspots are, next we will go, what is sunspot, we will see. Solar differential rotation. As I pointed out, sun is a gaseous object, it is not a solid object. And so sun, it does not have a uniform rotation, it has a differential rotation. It has a differential rotation. See, at the center, that is at the equator, sun rotates faster. You can see once in 25 days, sun is rotating, but the sun is rotating slowly here at the polar regions. Okay? So this differential rotation, here the material is completely plasma again. Okay? And then inside convection is taking place. So a sort of a Faraday effect, dynamo effect is taking place. The combination of the differential rotation and the convection. Okay? The rate of change of electric flux will produce magnetic field. So that is the Faraday's law. Okay? So because of that, what happens actually is the sunspots are produced. The sunspots, you can see the sunspots, and now you are able to see the sunspots moving from east to west. That shows that sun is rotating from west to east, exactly like the earth. Now in the earth, you are able to see the objects are moving from east to west. Exactly like that, you are able to see the sunspots moving from east to west. It shows that sun is also rotating, but that rotation is not uniform. At the equator, it is rotating very fast, whereas at the polar regions, it rotates slower. And this differential rotation consisting of the charged particles, ions, charged particles in the form of plasma, coupled with the convection. that is taking place from beneath produces activity on the sun, magnetic activity of the sun. And this magnetic activity is the most important one for any of the physicists to study. Otherwise, we will not show any interest in physicists or electrical engineers and so on and so forth. They will not show any interest in studying the sun. Now, this is one of the latest sunspot which you have seen, or you are able to see. And this sunspot can fill in nearly 40 years. 40 years can fill in the sunspots. There are several spots. This photograph has been taken with the period of sunspot maximum, sometime in the year 2006. And now, another one you can see, there are no spots, quite sunny. So, the sunspots, they appear and disappear gradually. How they appear and disappear, that's a big question to be answered with. Anyway, that can be taken up as a serious problem if you would like to do PhD. And now, sunspot cycle. Once in 11 years, you will be able to see more sunspots like this. Everywhere, sun space will be completely filled with sunspots. And once in 11 years, you will not have any spots on the face of the sun. Now it is declining. 24th maximum was over in the year 2012. Now it is declining. And again, it is going to approach the next cycle, 25th cycle. Now, this is 11-year cycle. The time between successive maximum is 11 years. The time between successive minimum is 11 years. This is called the solar cycle. Okay? And now, from the photosphere, when you go up, you will enter into the next atmosphere, which is called as chromosphere. You can see the chromosphere. The thickness of the chromosphere goes up to 10,000 kilometers. The temperature is 10,000 to 20,000 degree Kelvin. You see, as you go away from the fire source, fireball, sun, the temperature increases. It should not be, because as per the second law of thermodynamics, what do you know? Heat can be transported only from the hotter region to cooler region, unless some external work is done. Okay? So that external work done is the magnetic field. And because of the magnetic field, now, but are we able to say precisely whether it's only because of the magnetic field? No. No. There are various other factors, like acoustic waves, like gravitational waves, and then the magnetic field. It plays a major role. It plays a major role. And all these factors, they dump the energy outside. And because of that, as you come away from the sun, the temperature increases. It goes to the level of around 10,000 to 20,000 degree Kelvin. And so when you take the picture of the sun in H alpha, you are taking in H alpha, you know, in Lankavi, yes. The features are seen like that. And another one, calcium K, the features are plages and the filaments, they are all able to, you are able to see. And these are all active regions. These are all connected with sunspots. These are all connected with magnetic activity of the sun. Okay? So in that way, so the sun, you will be able to find. And now you may ask, when you have so many wavelengths, even in the visible band, from 3,800 angstroms to say around 7,200 angstrom, more than 20,000 lines are available, front of lines are available. Why are we choosing only these two lines? In the sense, these two lines are the strongest lines and sensitive for the magnetic field. If you take H alpha, in the case of the sun, the wavelength is 4 angstroms. Equivalent width of the line is 4 angstroms. 65, 63. It starts, the wing of the line, it starts 2 angstroms before, it goes up to 2 angstroms beyond. So such a broad line. If you take the calcium K, it is furthermore, it is approximately 20.5 angstrom. A very broad line. So these broad lines, they are sensitive for magnetic field, and that's why you are able to see the magnetic features here. And any star which are very strong in showing the H alpha and calcium K, they can be easily identified as sun-like stars. Okay? So these two lines when you take, they are able to show precisely the upper atmospheric conditions, chromospheric conditions on the sun. The next one is corona. What is corona? Corona means it's in Greek it is crown. It is just like a crown. So when the moon comes exactly in between the sun and the earth, moon is 400 times smaller than the sun, but at the same time 400 times closer to the earth compared to the sun. 400 times smaller, but 400 times closer. That's why sun and moon, they look similar angular dimension to our eyes. They look same size to our eyes. At times, when the moon comes exactly in between the sun and the earth, then the sun is completely covered, and we call this phenomena as total eclipse. And at that time, photosphere and chromosphere are covered, only the corona is visible. Corona is the outermost atmosphere of the sun, visible during eclipse, but you can see the temperature shoots up high. In the chromosphere it was around 20,000 degrees, but once you enter inside the corona, it goes to the level of millions of degrees, where gamma rays, X-rays, and then radio waves, they are all generated. What is radio waves? When the charged particle is accelerated through a magnetic field, then radio waves are produced. Okay? So radio light is produced. Okay? So all these radiations are produced in the upper atmospheric levels of the sun. Now, you don't need to wait for the eclipse. If you go to space and put a filter, then it will be possible for us to study the corona all times. One thing is, you will have to station your coronagraph at one of the Lagrangian points. Which is at a distance of around 150,000 kilometers from the surface of the Earth. There are 5 Lagrangian points. And at that point, if you go 24 hours, you will be able to view the sun. 24 hours. And when you view the sun, then the corona itself, if you take the picture of the sun exactly like the chromosphere, then a particular wavelength in X-ray, if you take the picture of the sun, it looks like this. And here, you can see the bright and dark magnetically active regions. And this is called as coronal hole, from where the materials are thrown out, which is very important for space weather. And then this is, again, this is a loop-like structure which may blast at any time, producing solar flares, throwing billions of tons of materials into space. And these are the magnetically active regions. See, if you take the coronal hole, it's a unipolar region. Where is the other polarity ends? If you say magnetic field, then you need to have two polarities. It's a unipolar region. If you see the magnetic field of the coronal hole, it will have only one polarity, the other polarity may exist elsewhere. And these are all the factors challenging to the laws of physics, laws of science, what we know. And that's why still people are, they're more inquisitive to study about the sun, so that, better science can come out. Okay. The next one is, see, now we are entering into the space weather program. So in the space weather, the first one is, I think I can. The space weather is nothing but the enormous amount of radiations and as well as the material that are coming out of the sun constantly. Every day it comes. Enormous amount of, we all know the radiation comes every day. It travels at the speed of light, 3 lakhs kilometers per second, covering the Earth, sun at the distance in a matter of 8 minutes. Okay? But what we do not know is the particle, that is, the material is also thrown out. The material is thrown out, so the constant emission of energy and as well as material from the sun, it is going to affect the Earth's environment. So the space around the Earth, that is called as the space around the Earth and the sun, that is called as the space weather. The weather that is prevailing in the space between the sun and the earth is called as space weather. That we are going to see. And what are all the factors that are going to affect the space weather? The first one is the solar This is solar flare. You can see the solar flare. The sudden outburst of energy. You can see the one sudden outburst of energy which is observed at Kodaikanal with the brilliant emission that shows that the material above the sunspots, they are blasted. They are blasted and they will be amounting to billions of megatons of TNT. So generally when a bomb is exploded, TNT bomb is exploded, we call it as 1 ton of TNT. 1 ton of TNT is equal to 4,184 megajoules of energy. Megajoules of energy. Now this one, or I can simplify in this way, it is amounting to thousands of atomic bombs. The energy released will be thousands of atomic bombs, and in between the sunspots, suddenly, that is on the neutral line of the sunspots, then what happens is an explosion takes place, and once that explosion takes place, it's called as a solar storm or solar flare. Okay, so materials are ejected out, and the temperature goes to as high as 50 million degree. 50 million degree. At 50 million degree, what will be the kind of particles? Everything will be in the form of charged particles. Charged particles. These charged particles, when they are moving, they produce what? Radio waves and as well as high voltages also. High voltages also. Very high voltages and very high currents. The voltage may go to the level of 50 million volts, and the current will go to the level of the movement of charge carriers is current. Agreed? Yeah. So the voltage will go to 50 million volts and current to the tune of hundreds of thousands of amperes. Hundreds of thousands of amperes, this blast. So such a huge plasma, ball of plasma that is ejected out, and the material density, material weight will be billions of tons of materials. Billions of tons of materials will be thrown out, and the entire material will be composed of charged particles carrying a very high voltage and current. And so if they strike the earth, what will happen? That's what we are going to study. That's what is called as space weather. And now the H-alpha flare, because why I am showing this in the sense, these are the things which you can observe from the ground level. The solar flare that can be monitored from the ground level in H-alpha. You can see, these are the things, and this is from the space. Okay, this is SOHO, extreme ultraviolet, the close to X-ray, this is 195 SOHO spacecraft, and from which this photograph has been taken, the flare. You can see the flare, solar burst. And now the flares generally they occur in between the opposite polarity. See, you can see the polarity structures P1, P2, here it may occur, or P3, P4 it may occur. So as the sunspots, they keep rotating, keep changing, as sunspots continuously grow. You see the sunspot, here you can see there are no sunspot at all. There is no sunspot on the previous day. The next day the sunspots have come, suddenly developed, and it developed as a big group. And now it starts growing or it is decaying. Either when it grows or when it decays, then what happens is you can see the change in the orientation. Are you able to see? Yeah. The change in the orientation you are able to see. So this change in the orientation, it creates a form of a twist, magnetic twist. And you take a rubber band and then you keep on twisting it, and once the twist exceeds certain value, the rubber band will be thrown out. Exactly like that, what actually happens is, because the magnetic twist, what happens is the energy is accumulated in the particular location on the sun, and that energy, once it becomes untenable, then what happens is it is released in the form of flare, or it is released in the form of so by constantly monitoring the opposite polarities, it is possible for us to study the flare phenomena. And now we have taken up two polarities, two opposite polarities, joined together. This is the east and west, and this is the north and south. Okay, and you see, the earlier one I have shown east here. Now I am showing east here. This is the way with which Asians represent the East and West. And that is the exactly opposite way the Westerners, they represent West and East. Okay, this is the true East actually, true East. So now, you can draw like this, and then it will be meeting the North-South, and then producing an angle theta. Any variation, the next day, if you see the sunspot, the same sunspot has moved here, and you can see the theta here, and there is a variation in the angle theta, and this variation in the angle theta may represent the twist. That's what we have identified. And once the twist exceeds the value of very high, once the twist becomes very high, then you can see when the twist happens to be around 20 degree, a brilliant flare has been observed. A normal flare has been observed when it is between 10 and 15, and then the normal flare, and then the sub-flare is produced when the twist exceeds 5 degree. This is the threshold limit for the flare. So, and of course, high cadence, high time cadence observation is needed to continuously monitor the sunspot. That is, you have to monitor the sun in white light continuously at least every second. Of course, nowadays you have CCD and other devices through which it will be possible for you to take the picture of the sun in every milliseconds. Then it is possible for us to see at what time the changing orientation it is taking place. The twist is developed. At what time the emerging of flux is taking place. At what time the submergence of flux is taking place. Okay? And now this is another one. Flare we have seen. This is the next one is coronal mass ejection. And it is slightly different from flare. It may be associated with the flare, but sometimes without the occurrence of flare, the coronal mass ejection is taking place. And a huge volume of material will be thrown out without the flare, occurrence of flare. But sometimes, along with the flare, this coronal mass ejection will be taking place. And the process of occurrence is at least one per day. During the period of solar maximum, it goes to the level of even 6 per day. You can see the rate of mass flow, it is 200 million kilograms, a huge volume of gas, completely filled with charged particles. They just come. And kinetic energy is tremendous. And the average time to reach the earth is, the particle speed is of the order of around 1000 km per second. So the time taken for the particle to reach the earth is 3 to 4 days. Okay? And this is what is called the space weather, which we talked about. And this space weather refers to the violent transfer of energy and as well as particles from the sun towards the earth. And now, the next one, the next phenomena is solar wind, which is constantly taking place. Solar wind originates from the coronal holes, which we have seen earlier, coronal holes. And now, when the this is a solar wind that is coming from here. Why it's not working? I don't know. Is it coming right from the pen drive?
Coming. Okay.
Yeah. Now you can see the solar wind is coming and it will be entering through the magnetic fields of the Earth's atmosphere. Now Earth is coming and magnetic field, through the magnetic field lines, it is entering through the atmosphere, through the, these are all the magnetic field lines. So they join with the magnetic field lines, the material, and then you can see the spark, a huge spark, 50 million degree, and then hundreds of thousands of amperes. It creates a huge spark. And then what will happen? And it's almost a place like Canada. And then the entire power grid will be shut down. So because the transformers there, which is generating power, cannot withstand the voltages to the level of 50 million voltages and hundreds of thousands of amperes. And so they will be short-circuiting these transformers. In Canada, the temperature is minus 40 degrees always. People think that, because the pay, what they are getting, more attractive, life will be very easy there, it's very tough. Most of the time it will be to the level of around minus 10 degree. And most of the time it will be minus 40 degree. And in Malaysia, you have a wonderful climate. Okay, and if you want, you can go out at any time. You can go out and then you can talk with your friends, and then you can, wonderful climate. Neither like India where the temperature is extremely hot. Okay, here also it's hot, you complain. Malaysia, it's hot like that. Okay, because you are used to AC. Okay, that's why you complain that it's very hot. In Canada, imagine that if the power goes, then what will happen to the people? People will suffer. And because room heater is needed all the 24 hours. Don't think that, that is Canada, you get a lot of money and so life will be easy. Life is extremely tough. In United States also it's like that. It is like imprisonment. You have to confine yourself within the house. Okay? And if you may get a lot of money, but you cannot move anywhere. Okay? So, and in such places, high altitude belts, if the flare comes, then where the flare, earth is like that, and high altitude they are exposed. And the high altitudes when they are exposed, those places are prone for the attacks due to the space weather. So, in Malaysia, you may say that we never experienced such a kind of a thing. In India or Malaysia, I'm sorry, I don't know what to mention about Malaysia. In India, if it happens, to restore the power, it will take at least few years. Okay? In Canada or in United States, they try to restore it in a matter of few weeks. But in India, it will be extremely difficult. It will be extremely difficult to restore the power. Fortunately, India is exactly on the equator. Always it is summer. There is no winter at all. Always it is summer. Compared to India, Malaysia looks better. The temperature is not very high here. But even then you may complain that it's very hot. Okay. If you come to India, then you feel that it is very hot. But if you go to Canada or United States, you may think that it is better to be in Malaysia. You can go to the street and then you can have food all through the night. Okay. So there you cannot go, you cannot walk. You cannot walk. To get inside the car, you have to run. You have to run and then get inside the car. Completely you have to cover, only eyes will be open. Your nose also you have to cover. So that is the condition. And so there if the electricity goes off, then what will happen? It will be a chaotic thing actually. And so another one is, such a huge amount, knowingly or unknowingly what we have done, we have installed many spacecrafts. Each spacecraft cost a minimum of $400 million US. Big money, big money. It's a big money. So when such a storm, when it comes, then what will happen to the spacecrafts? Gone. So we will have Deepavali there. Yeah. Okay, in the space. Yeah. And then once these spacecrafts goes off, then what will happen? Your television will not work. We will be missing the cricket match or we will be missing today's serial. Okay, you have serial here? In India we have a lot of serials. Okay, and then matches, cricket match or football match and all those things you cannot watch. And then your mobile. Everybody is having mobile. And people are talking, 48 hours in one day. And if you ask whether such a top-up is available, yes, it is available. That's what they say, service providers. And they are all done through the satellites. And if the satellite goes off, then what will happen to this?
Nothing.
Leave apart. And then airplanes from Trichy to Kuala Lumpur. I am from Tiruchirappalli, and I come from Tiruchirappalli to Kuala Lumpur. And you have a lot of airplane services are there. And they are all controlled by GPS and not by...
all satellites.
So GPS is what actually? Every continent you have 6 satellites launched. Now they are going to increase it also further. Sure. And so the and then the altitude at which the plane flies, it's around more than 34,000, 35,000 feet. So that if you go at a very high altitude, then the fuel will be reduced. Once the fuel is reduced, the fare will be reduced. Everybody can fly. Agree? So that is the process. Okay? And that is why, that is the hotel where I am staying per night, that is a fare, that I paid, to come from Trichy to this place. It's cheaper, So, when you would like to travel from Kodaikanal to Bangalore, you can travel from Trichy to Malaysia, another country. So, and now if the GPS works out, then the pilot will be blinking where to go. Okay. So he will not know. So it is always, it becomes essential for us to monitor the sun to protect all these events. And not only that, even in many places, for example, the gas or oil pipeline, which you see, the oil comes through pipe covering from various areas. In high latitude belts in United States and Canada also they are doing it. And the gas connection, now we have cylinder at India. What about here? Cylinder only? But there it's not cylinder, it's a pipeline. So it's coming through pipeline. And it is transported underground. When that comes and hits the ground, then what will happen? That's all. Everything will be blasting. Okay? Just like a bomb. And so life will become extremely difficult, and that's why to monitor these solar events, energetic events, and we need to have a lot of youngsters. So that the energy takes 8 minutes, but at the same time, the particle to reach, it takes 3-4 days. So if you can monitor and then inform that, then what we can do is, at a time when lightning is there, yesterday lightning was there, lightning is there, if you conveniently watch your television, sometimes it goes off. Okay, where lightning enters either through the antenna or through the power pole. So because of that, what happens is 20,000 voltage will be developed, and thousands of amperes current will be developed, and that your set cannot withstand. Even if there is no power, that will enter and then create a spike. And because of that, the television set goes off. Exactly like that, if it happens there on board, there on the satellite, then what will happen? That satellite has to be abandoned. And one cost around $400 million US. And that's why, especially in America and Europe, to safeguard all these satellites, they need to have youngsters to study the sun. And these people can monitor, and then they will be telling that, you switch off. Switch off the satellite momentarily. And when you switch off the satellite momentarily, you are trying to save the spacecraft. Exactly. When you disconnect your television set, and then your television set will be saved. Exactly like that, we can do that. And also now, the technology has been so much advanced. Now for the further satellites which are sent, a bypass capacitor you can attach, so that the surge current can be bypassed. Okay. So in that way, and now the space weather, it is offering a lot of avenues for young people. That's why to Farana, she was suggesting me that if you can give a talk of the same, because one of the paper she has utilized for her work, and then she was telling me that, can you please come and deliver a talk, so that space weather, can pick up here in Kuala Lumpur. And of course, only thing is, in India or in Malaysia, I doubt whether you will have a lot of avenues for this field, but in United States and other places, in Canada, Canadian Space Agency and NASA, you have a lot of chances. And because they are the people, who have a lot of satellites abroad, a lot of satellites on board, and so to safeguard all those satellites, they need to have youngsters. And so you will have a lot of avenues. The next one is, this is what? When they enter, see, this is space weather, this is the Earth, this is the central point of the central point is the Earth, these are the magnetic field. When they come and hit the Earth, then the magnetic field lines becomes like a bow shape. and here it will experience a shock which is called as bow shock. Okay? As it enters through the bow shock area, and then when it goes through, the velocity of the materials will be reduced, and so here you will get a turbulent region, and that region is called as magnetosheath. And then beyond this beyond boundary also it may try to enter if it is more powerful, the blast is more powerful, and then it enters here, and this is the boundary, and where the magnetic pressure balances the solar wind pressure, and because of that, beyond this it may not pass through. But the event is severely powerful, then it will pass through and reaches the earth, and now this is the earth. Unfortunately, we are in the center of the earth, so nothing happens for us, but whereas in the polar regions and all, the devastation can occur. Okay? And sometimes what will happen in the sun, this is the event, this is the flare, and now you can see the aurora, you can see, the power grids will be affected, auroras you can see, and see when they enter through our magnetic field lines and then interact with our atmosphere, then they produces colorful lights in the sky, which again, you may not experience it here in the equatorial belt. You may be able to see every day in US and Canada. Okay, and so since sun is by far the largest supplier of energy to the earth, any energy imbalance of the earth will affect the energy balance in the earth. That's why it is important for us to study the sun. Also, sun climate connection, that is also sun earth climate, and that's a must. And the space weather, it becomes important to study the space weather, which we have seen. And then sun as a star, and sun as a physical laboratory, because there are a lot of things which are happening there, and the sun still we are unable to understand those processes, and that's why sun itself can be taken as a laboratory where we can test our laws of physics, where we can know more physics on that, through that. This is the astrosat, and this is the Hubble Space Telescope. Some of the pictures of Hubble Space Telescope I will see. The Space Telescope has been launched in 1990 at an altitude of 593 kilometers, 600 kilometers above the surface of the Earth, and through which the space photographs have been taken. This is Hubble. One of the beautiful picture of the Hubble. This is a galaxy at a distance of 28 million light years. Again, nebula, which is a distance of 3,000 to 6,000 light years. Another nebula, colorful nebula. Okay, this is at a distance of 5,000 light years. Cat's Eye Nebula, and now Hourglass Nebula, that is a distance of 8,000 light years. Cone Nebula, 2.5 light years away. And then a beautiful picture called Starry Night. Two galaxies colliding each other. It's very rare, and that has been photographed by Hubble. More pictures from Hubble. This is a Voyager which was sent in the year 1973, and in search of life somewhere else. And where is the position of the Voyager? Now it has crossed Pluto. And now another planet which has been discovered by Hubble and Comet Halley, and a protostar. Just before a star is completely formed, the materials are sucked in, and a protostar has been photographed by Hubble. Another galaxy, Earth with clouds, Earth without cloud, Earth with new moon, Earth with full moon, Sun with atmosphere, Sun without atmosphere. This is Venus with clouds, Mercury, Mars, two satellites of Mars, Jupiter, and then the satellites of Jupiter, Saturn, satellites of Saturn, and then Venus, satellites of Uranus, satellites orbiting Uranus, Neptune, satellites of Neptune, Pluto, satellites of Pluto, Milky Way. Now, words are becoming, this is the galaxy. Words are becoming meaningless when we are confronted with such monuments of light and color where stars are going to be born. Who knows? Many stars are going to be born here. And so, is this the end? I'm not sure this is the end. Thank you. If you have any questions,
So, thank you very much, Professor K.Sundara Raman. Now I would like